All right, everyone. In this section, we are going to discuss timber decking. And the applicable details for timber decking are going to be our W1 and 1C, 2 and 2C, 3, 3C, and 3E, with the 3E being the Eswatini specific deck board detail, and then W6 and 6C. And I've noted here which portions are timber. So either the crossbeam can be a timber member or the decking can be a timber member or lumber. So first, I just want to discuss give a reminder about the stresses or the load on these beams or members. Remember from before, we calculated our M and our V, and that would be the maximum depending on the geometric conditions. So M max and R max, using the equations from the previous lecture, and those will be linked in the notes for this section as well. But using those equations to calculate an M or a moment and a V or a shear. And remember, we're not combining the point and distributed load at the same time here. We're checking them as two different scenarios. And just another note for you here is to remember to add deck weight when we're looking at the cross beams. Remember the beams themselves or the deck boards themselves are only going to be seeing that live load. But the cross beams will potentially be seeing the load of potentially the deck board, the nailer, and the weight of the cross beam itself. So what we're going to have to do here is include a plus W deck term, and you should have already calculated this from the load section of this course way back. When you calculated the actual dead load of the bridge, you probably have this component waiting for you in your spreadsheet, hopefully. If not, it's worth adding. So as a reminder, we'll have our live load plus our deck load for the cross beams, and we'll have our live load, just our live load unreduced for the deck boards. So the first step we're going to go through here is in the NDS. I'm using the 2015 just because it's the easiest to view online. You can just Google that, or I will link it in this file below, or in the module below. And the two important documents here are the Nds Supplement, which will give us properties and some adjustment values, in the manual, which will tell us how we're doing our checks and adjustments. So first, we can take a look at using the W1 detail as an example. In organizing the geometric properties for the deck board and crossbeam, we can look at a section which is going to be depth by breadth. Here in this diagram, we'll show you what is breadth and what is depth. And for some of the adjustment factors, these are interchangeable. And based on the properties of the beam, so how much wood is actually there, how much timber is resisting the load, we can calculate a moment of inertia and a section modulus using these two equations. And the reason I'm calculating them instead of just using the Nds Supplement Table 1B is because we have the centimeter values and they don't necessarily correspond to perfect sawn lumber values from the US that we use. So it's more accurate and we can get more capacity by sharpening the pencil and calculating this value. So moving on, we will go to step 2, which is using the Nds chapter 3.3 for bending members to find our actual stresses, which will be lowercase fv and lowercase fb. And notice how they're calculated with here the section modulus and that BD term. So it's relating the V and M values that we found previously based on the geometry to what actual stresses the beam is going to feel or the deck board is going to feel. And we need to then make sure ultimately that we have the capacity to resist these actual stresses or our demand loading. And finally, we'll find our capacity, which is F prime, capital F prime B and capital F prime V. These values here are what you should start off with, 1.44 and 3.96 megapascals. And note that they are subject to change as we are gathering more information about the actual species of wood that's getting used in our countries, which that information has been hard to track down, and I'll add to the comments section what values to use once those get updated. And as you notice, if you scroll through the NDS supplement, you can see hundreds of different values for various species of lumber. So based on table 4.3.1, here are our adjustment factors for our bending and shear stresses. And I'll go through these one by one. So first, our load duration factor can be found in section 2.3.2. That will be 1.0 for a occupancy live load for our distributed load. And we're going to call that 2.0 for our point load to give us a little extra capacity, because it's likely that's going to be an impact loading, and wood is much stronger in impact events versus over long periods of time. But note that that does get reduced to 1.6 based on note 2, because we're going to assume that our wood, because it's outdoor use, is pressure treated. That could get updated based on the information and will be posted below. Next, we'll talk about CM, which is our wet use factor. This should be 0.85 for bending and 0.97 for shear based on table 4A in the supplement. But if you see note 1, we can bring that to 1.0 for bending because we are assuming such a low capacity of the wood, and the combined multiplication of our FB value times our shape factor or size factor, which I'll talk about in a moment, is less than the value that it needs to be, so we can bring this to 1.0. Next, our temperature factor and our incising factor are both going to be 1.0. The reason it is 1.0 for the reason is that 1.0 for the incising factor, even though we're assuming it's pressure treated, is because that pine is not likely incised when it is pressure treated. So moving on, those are all the factors for shear, and we're just going to discuss the ones that are bending only to finish up. The beam stability factor does not apply here, and that's going to be 1.0. And then the size factor is a little more complex. Depending on the crossbeam and the deck board, these are going to be different values, and depending on the walkway detail we're using, different size crossbeams, these are going to be different values. So note these values of 1.5 and 1.2. They can be slightly different depending on the detail, and also note that order does not matter when using these tables. So if you are using 2 for depth and 8 for breadth, and that brings you off the table, just swap that and use 8 for depth and 2 for breadth to get your value. Next, we'll discuss flat use factor. So that's when the beam is loaded, or the deck board is loaded on its wide face, like this. So once again, we can swap the values back and forth in this table here. As long as it's being loaded as it's being loaded on the wide face, we can take 1.1 for the crossbeam and 1.15 for the deck board. And remember, these are specific for the W1 detail. All of these factors that I'm going through right now are just as an example with the W1 detail. And finally, we'll talk about our repetitive use factor. Section 4.3.9, we find that we can use 1.15 for the deck boards because of their proximity. Being less than 24 inches on center, they're actually touching, so we can definitely use that. And we only get to take 1.0 for our cross beams because they are not close enough to qualify for the repetitive use factor. And finally, we'll want to take our calculated F prime capacity value and divide it by our demand, F, lowercase f value, and we want to make sure that value is greater than or equal to 1, and that's our demand capacity ratio, which is no different than ASD design we've discussed in the past. In the past, we would have some factor of safety applied, to that demand. And in this case, following the NDS, those factors of safety are already applied. So we just want to make sure we have a greater than or equal to 1 value there. This would also be like our calculated factor of safety.